So if there is any question, Uday, if you could pass this along to me, that will be great. And thank you for helping me out with the class today. So before we uh, begin, I would like to sign off from my laptop and just use my iPad because I'm hearing an echo. You're probably not hearing this, but this is very confusing. So give me one more minute.
So one last time, Uday, can you confirm that you can still hear me?
Yes, yes, we can hear you. Yeah,
All right,
good.
all right. And my screen is visible now, right? Because I just signed off from the uh,
Yeah,
computer.
yeah, all good. Yeah, screen is also
All
visible.
right. Thank you so much. First of all, have we started recording already?
Yeah, yes, I have already started the recording. Yeah.
All right. Thank you. Thank you. Hello, everybody. I'm sorry that I couldn't, give you a heads up about it. I had an invite to come to give a lecture in National University of Singapore and at an international conference at Singapore. Like basically two lectures. I tried to skip them. I tried to, find ways to do it virtually, but in the very end, we realized that there is no other option. So, I had to make a call, and I basically just booked my flight ticket the day before my lecture, and it was a last moment decision. So I couldn't plan ahead of time. I'm sorry for causing any inconvenience, and I appreciate your cooperation. In the last class, you must have gone through a tutorial on TCAT Centaurus, and I'll be happy to answer questions when I come back about that. But I do recommend that uh, please try it out at home whenever you find the time. It's one of the most cutting edge tools that semiconductor industry uses to actually design devices and material device interfacing for next generation IC design. So hopefully that will be of interest to some of you in future. Without further ado, let's get started with the technical part again. I do realize that we started this lecture 9 and we went through a few slides, but then there has been a gap. So I want to quickly review a few things to put things into proper perspective. So in this slide, we first identified the type of symbols that we'll be repeatedly using. And just to quickly remind you, N represents number of electron. Basically, it's number per unit volume of electron. P represents number of holes per unit volume. And when we add a zero to any of them, it represents number of electrons at thermal equilibrium, number of electrons per unit volume at thermal equilibrium, number of holes per unit volume at thermal equilibrium, right? Zero represents thermal equilibrium. And what is delta N and delta P? It represents the excess electron and excess hole concentration generated due to some sort of external excitation. And N and P represents the total electron number and total hole number. So basically N would be N0, whatever you have during thermal equilibrium, plus delta N, the excess carrier that you generate through external stimulus. Okay? So that's the total number of electrons available in a system. Similarly, for holes, it would be P0, thermal equilibrium number, plus del P. So we identified all of them. And then we also talked about generation rate, recombination rate. G represents generation rate. Gn is for electron generation. Gp is for hole generation. And we use prime to represent it's a rate, like it's per unit time. It's just a representation. For recombination, we use uppercase R, recombination for electrons and recombination for hole. And to represent that it's a recombination rate, we use prime. Finally, tau N and tau P is the excess minority carrier lifetime. So this is lifetime for electron, lifetime for hole, but we have to remember only the lifetime of minority carriers will be relevant to our calculations and discussion. And I think I explained the reason for that. Maybe I'll review quickly in the next slide. So here we talked about carrier generation and recombination in equilibrium. So in thermal equilibrium, we generate electron hole pairs in pairs, basically. So whenever an electron goes from valence band to conduction band, you have one electron and one hole generated. So they are created in pair. So their generation rate, the generation rate for electron and hole at thermal equilibrium should be equal. And one more thing, when an electron decides to go back to the valence band and give up some energy, say, it will annihilate the hole in the valence band and it will annihilate itself. So apparently this electron hole pairs will be annihilated in pairs as well. So apparently the recombination rate for electrons and holes will be the same. So that's what you see here. This is in thermal equilibrium. Now, in case of some sort of external stimulus, like for example with light, there is a new set of carrier generation that occurs, which is basically excess carrier generation. And they are also created in pairs, as you see, an electron going from valence band to conduction band directly. And that's why it's called direct band-to-band generation. I'll talk about recombination in a second, but direct band-to-band interaction. So it goes directly from one band to the other band. And at some point, you'll see there are other possibilities as well. You don't necessarily always need to send electrons from valence band to conduction band. But for simplicity, let's just stick to this one. So this is direct band-to-band generation. And just to quickly also show you, this excess carriers could also recombine directly. Whenever you excite electrons, they go up to the conduction band, but they can always give up that energy and go back to the valence band again and recombine with the holes that they generated eventually. Now, as you notice, this number of electrons generated and number of holes generated, they are basically equal for excess carrier generation. I want to also highlight one more side here. Imagine, I mean, whenever you see N0 and P0, that represents thermal equilibrium. So at thermal equilibrium, you already have some electrons and you already have some holes. And you might be wondering, and I'm sure I discussed this, but why do we have a difference in the number of electrons versus number of holes? Remember, in thermal equilibrium, you have electron hole pair generation. So there is a, 1:1 correspondence there. But you could also create extra carriers by doing what? By doping. So if you use N-type doping, for example, you can always create more electrons than holes. So, but this is also thermal equilibrium. You're not applying any external voltage or external light or anything else. You're just doping the semiconductor and thereby creating an excess, number of electrons. So when you see more electrons in a system than holes at thermal equilibrium, that represents that it's an N-type semiconductor. Now, what did I tell you about total N? The total N would be whatever you had at thermal equilibrium plus whatever you generate as excess carrier. That's the total electron concentration, and similar for total hole concentration. All right. Now, when you calculate the recombination rate, as you see, the recombination occurs in pair as well. So the number of the recombination rate is related to the number of excess carrier. And there was a question in the last class, I forgot to clarify that later on. So why are we using delta N for both N-type and P-type semiconductor? Basically, delta N and delta P should be equal because they are generated in pairs. So it doesn't matter which one we use, right? But while calculating the recombination rate, the time component, the lifetime component will have to be considered carefully. So for P-type semiconductor, you have a lot of holes, but you don't have that many electrons. So electrons are minority carriers. And I told you minority carriers will be the bottleneck. Imagine you have 1,000 electrons and just 10 holes, right? So then you cannot recombine all 1,000 electrons at once. You can recombine at most 10 electrons at a time. Maybe after recombination, there could be new hole generation and then more electrons can recombine and so on. But the rate will be determined by whoever is smaller in number, right? So the minority carrier number will determine the actual rate of recombination. That's why for P-type semiconductor, where electrons are minority, the time that you use is the lifetime for minority carrier electron. And similarly, and 0 represents like a thermal equilibrium situation. So for N-type semiconductor, it's the opposite. For N-type semiconductor, holes are the minority carriers. So the lifetime that you use would be that of the minority carrier lifetime of the hole. All right, so moving to the next one. This is a new slide, which we didn't discuss this in the last class. So here we will discuss the concept of dielectric relaxation time constant. So apparently, when you inject, all on a sudden, when you inject a set of excess carrier in a semiconductor material, the material tries to balance the excess charge. Okay, because remember, whenever you have an excess of a certain number of carrier and you don't have the opposite kind screening the charge, there will be an increase in energy. The material will be unstable energetically, right? For that moment. So the material, if possible, will try to counterbalance that excess charge by creating opposite charge inside it. You might be wondering, why didn't that happen here? Because remember, you were creating electrons, but there were equal number of holes screening out the effects of extra charge, right? So in terms of charge balance, the material was always balanced actually. It had the exact same number of negative and positive charges within itself. But imagine, instead of generating this excess carrier in pairs, what if we could inject a set of excess carrier? Like maybe we inject a set of electrons or inject a set of holes, right? That means they're not created in pairs anymore. They're being injected somehow. And we'll see very soon how that injection works. But for the time being, let's assume that we are somehow managing to inject. So this is an N-type semiconductor. We're injecting some excess carrier holes. So delta P represents the excess carrier, and we are injecting the holes in the N-type semiconductor, which is obviously the opposite type. So this semiconductor will try to do something to counterbalance the excess charge and eventually relax. Okay, so that's why this is called the dielectric relaxation time constant. And let's talk about it. And the way we calculate the relaxation time is by using three equations: Poisson's equations, Ohm's law, and continuity equation. And this is a simplified version of the approach. This is easy enough to discuss, so I decided to add the math. But in the end, this is all that matters: the time constant. So where do you have a time constant? Imagine when you're trying to charge a capacitor. Say the capacitor cannot just charge up directly. Say the voltage across the capacitor being, say, VC with respect to time, you cannot just abruptly charge up the node voltage of a capacitor. That's impossible, right? You have to gradually charge it up, and then it also discharges gradually, as you know. Why? Because there is a time constant involved in the charging process and a time constant involved in the discharging process as well. Okay, the time constant could be tau. Tau charging, tau discharging, say. So whenever there is a time constant associated with the charging and discharging process, you can understand that there will be a delay in the process. So you have to wait for a certain amount of time to let it finish its job. So similarly, through this calculation, we will end up at a situation where you calculate a tau, a time constant, and the time constant is related to epsilon, the dielectric constant of the material, which is, a given property for a given material, and sigma is the, conductance. So apparently, using the conductivity as well as the dielectric constant, you could calculate how long it will take for the material to eventually relax in response to some sort of externally injected charge. And notice, this time constant is related to the material property. Okay, so keep that in mind. For different materials, this time constant will be different. Now, here is how we start. We start from Ohm's law, and I told you in one of the classes that Ohm's law, we no longer will write Ohm's law equals, Ohm's law represents V equal IR, right? We'll be using J equals sigma E, which is the more fundamental version of Ohm's law. It's current density, electric field, and conductivity. So if you take the divergence of this, and here is why we will take the divergence. So if you take the divergence in both sides, here and here, sigma being a constant, you can take that out of the divergence, and you are left with divergence of electric field, divergence of current density. Now, notice Poisson's equation, which somehow connects the electric field with charge density in a material. So this is the charge density within a material, and epsilon is the dielectric constant of the material. Okay, and the E represents the electric field within the material. All on a sudden, you notice that you could replace this delta divergence E with rho over E. So that's what we are going to do. So sigma was already there. You are just replacing divergence of E with rho over E from Poisson's equation. And again, you must have noticed I'm not talking about the origin of any of these equations, because I'm assuming that maybe in high school physics you saw that, but if not, it doesn't matter. That basically will not make too much of a difference in the future discussions that we'll be having. as long as you know that this number exists. But anyways, this is simple math. I want to go through this anyways. So you end up with this situation. Divergence of current density is equals to sigma rho over epsilon. And then there is this final equation, continuity equation, which is a little bit less obvious. So I have added a note about it. You can read it. But just to represent continuity equation, basically represents that a charge is moving out of a differential volume. Imagine if you have a tiny zone in space and charge is moving out of that zone. So this divergence of J represents the space, the change in charge. Basically, current density is nothing but flow of charge per unit time, apparently. So it kind of relates current density, change in current density, with the rate of change of charge density. Okay, so that's what the continuity equation does. But in a simplistic form, delta J is just derivative of charge density over time. All right, and you see partial derivative here because the process typically occurs in, you know, in 3 dimensions. But for all practical purposes, we could just ignore partial derivative and just treat it like a one-dimensional problem and just replace it with direct derivative. Okay. Anyways, so replace delta J with this form and replace this form with a simplified derivative form. Then you end up with a differential equation like this, and you can solve the differential equation, and you end up with a solution where there is an exponential term in the solution. And in the exponential term, you don't see that here. This is all taken from textbook, by the way. You end up with e power minus negative t over sigma over e. This is the actual term that comes. And we assume this to be the time constant. So whenever you have e power t over tau or negative t over tau, so whatever you have in the denominator with time represents the time constant. Okay. So we decided to start calling this quantity the time constant for dielectric relaxation. All right. Anyways, don't feel lost. If you feel, oh, if you don't feel so good about this derivation and stuff like that, it's okay. I'm happy to talk about it again when I'm back next week. So basically, I'll be catching a flight later today. So I came here only for a day, all the way from the US. So anyways, without taking a tangent, the point is, if you need more clarification, I'll be happy to go over the details of each of these and clarify. But for the sake of this course, we may not need it, as long as you understand that the dielectric relaxation time constant exists, and you cannot just arbitrarily counterbalance the injected charge. It takes some time for the material to balance it out, and here is how you can measure it. Let's go to a simple math problem to measure them. So consider an N-type silicon with a donor impurity concentration of this much. Calculate the dielectric relaxation time constant for this semiconductor. Sure. So dielectric relaxation time constant, as we have just seen, is a function of epsilon over sigma. And epsilon is a material parameter, like I said. And for silicon, it's pretty standard. This is the number. You can easily find it. Remember, this is K times epsilon naught. Epsilon naught is the permittivity of vacuum, and this is a universal constant. And K is the dielectric constant for silicon, which is 11.7. It's also standard. Don't worry, these will be given if there is ever any math questions. So these numbers will be given. No worries. But how about sigma? So you might remember, by the way, in textbooks, they represent it in different form. So what I just wrote before, K epsilon naught, in some textbook, instead of using K, they use epsilon r. Relative dielectric constant. Okay, instead of using K, they use epsilon r. So it doesn't matter. Maybe we might also give you epsilon directly so that you don't have to be confused with the internal calculations. But sigma, I hope you guys remember that we derived the expression for sigma in a way that E mu n plus E mu p, that was sigma. That was the conductivity of a semiconductor. Okay, and this is N type with just donor, and obviously this is an assumption. We can ignore the number of holes. I mean, basically that's what the textbook guys are doing. Basically, just ignore this, and then assuming that whatever donor you used, everything was ionized. So you have 100% ionization. because they haven't given us any other information. So assume that you had full ionization. So the number of electrons will be equal to the number of donors. So E mu and ND. That's what we do. And you see there is an approximation sign. Obviously, this is an approximation, but you could do a simple ballpark calculation and then put that number in and calculate sigma, calculate tau. All right. And I'll be posting a homework soon, and hopefully you have some more practice with this math problem, and hopefully that will prepare you well for your midterm moving forward. Okay, so moving to the new concept, quasi-Fermi energy level. Okay, we are heading there. But let me take a moment and see whether there are any questions from the class. Uday, could you pass them along to me if there are any questions? Because I cannot see anybody.
Is there any question? So I think there is no question. So yeah,
All
maybe you
right,
can.
all right.
Yeah.
Sure. Okay. Does everybody look sad or lost? Or what do you think? Are you guys following along?
Yeah,
I
they're
hope so.
following.
All right. I know it's not the most ideal thing. I hope at least I like looking at your faces. That way I can tell whether or not I should slow down or speed up. But here I'm kind of looking at my screen only. So please help me out. Let me know if you are for some reason feeling lost or feeling confused. I'm more than happy to go over this. And there is no rush. I hate rushing through the content. Even if uh, a few of you are feeling left behind, just speak up and I'll be more than happy to go over again at any part. Okay, so quasi-Fermi. We have talked about Fermi energy level before, but what is this quasi? Why is this quasi? Here is why. So I'm sure you don't remember this exactly, but if you could go back to one of the previous lectures, you will see we talked about this derivation. We talked about Boltzmann approximation, and we talked about how you can calculate the number of electrons and number of holes in thermal equilibrium. And that is related to the Fermi level and the difference between the Fermi level and intrinsic Fermi level, right? And these were all in thermal equilibrium, meaning you had conduction band, you had valence band. For intrinsic semiconductor, Fermi level would be in the middle, intrinsic Fermi level. But if you don't have an intrinsic semiconductor, maybe you have an N-type semiconductor, then this is your actual Fermi level, all right? So this EF represents the actual Fermi level. EFI represents the intrinsic Fermi level. I mean, if you had an intrinsic material, this is where your Fermi level would have been. And that applies to both equations. You can calculate the number of holes and number of electrons depending on these two relative positions of Fermi level. Okay, so the actual Fermi level. Now, remember, all of these were in thermal equilibrium. That means no external stimulus. But now that we're talking about excess carrier generation, there is a chance that we have either injected carriers externally or we have injected some sort of external stimuli that has created these excess carriers. Now, in that situation, how do we define Fermi level? This Fermi level was previously defined by the donor and acceptor in equilibrium. But when you all of a sudden inject charges or generate charges, this Fermi level will change. And I'll show you in the next slide a relative representation as to how that changes. But an easy way, this is more like an approximation, would be to, instead of just showing the thermal equilibrium number of electrons, you add an extra term. So basically, whatever number of electrons you had before, you add an extra excess electron number, and you get the total number of electrons. And everything else should remain the same, except your Fermi level should change now. Because of this additional electrons, they will slightly go up in energy, and the Fermi level will be temporarily set to a different level. And that different level is called the quasi-Fermi level. Why? Because after relaxation, this Fermi level will change, by the way. It's only momentarily that the material will have a different Fermi level when you inject the charge or when you excite the material. And then after relaxation, as you have seen, every material will try to relax eventually and counterbalance the excess charge if possible. And thereby, that Fermi level can change. Similar argument applies to holes. You just add the excess number of holes and you change the Fermi level. So the Fermi level was here. You don't change the intrinsic Fermi level, remember? The intrinsic Fermi level represents just a reference point. It's not really the real Fermi level because the material has been doped. It's no longer intrinsic. This is just a constant uh, you know point of reference, nothing else. But this Fermi level is not a constant. It changes, by the way. So that's what is changing between these two equations because of external stimulus. Now, let's see. This is actually the last slide of this lecture, and you can read through this later on. I'm just gonna explain these two diagram, and the explanation is also written here. Here is what we are looking at right now. So this is an N-type semiconductor. How do I know it? Because the Fermi level is closer to the conduction band, as you see. An intrinsic Fermi level is just a reference, point of reference, as you see. Now, what happens when you inject extra carrier? Maybe you have generated extra carrier, you have generated excess carrier. So when you generate excess carrier, there will be delta N and delta P. So you have generated additional electrons and additional holes. Okay. So here is how the situation looked like. This was the previous Fermi level. Let me just mark it with red. This was the previous Fermi level. I hope you remember this discussion. If I make the material more N-type, say somehow I increase the doping or I somehow inject electrons, I make it more N-type, the Fermi level should move closer to the conduction band. And I hope you remember that argument where we talked about if you keep doping the material heavily with N-type, the Fermi level at some point will get inside the conduction band, right? It will be so heavily doped that the level will go inside the conduction band. So the bottom line is the more electrons you generate, the Fermi level will gradually move closer to the conduction band. Okay? And you see there is a new Fermi level that has showed up. That's the quasi-Fermi level generated because of the excess electrons that you have created. All right. Next, remember, you have also created all on a sudden delta P with delta N. The delta P is an additional, hole concentration. And to represent that, we now use a different Fermi level for hole. So in the quasi situation, we use a different Fermi level for hole. We use a different Fermi level for electron. And let me explain one more thing here. So the difference between this Fermi level and the conduction band represents the total number of electrons available in the system. Similarly, the difference between this Fermi level for the hole, which is a quasi-Fermi level that we are drawing, and the valence band is related to the number of holes available. Okay, so the more holes you generate, the closer this level will be to the valence band. Okay, so instead of just drawing one Fermi level, we draw two Fermi levels for electrons and holes, and that's what this equation shows you. Just compare between these two equations before injecting excess charge. You had intrinsic Fermi level, and you had just Fermi level showing up. Sorry, I marked the wrong thing. So you had intrinsic Fermi level, and then you had Fermi level showing up in both equations because we used to use just one Fermi level to represent the electron Fermi level. That's all. And the same one could be used to calculate both holes and electrons. All right. But here, since we are using two different Fermi levels to represent excess electrons, and where did I go? In a second, for some reason it froze. All right, sorry, the PowerPoint froze. So I was gonna say that since you are using two different Fermi levels to represent the electron level and the hole level, we are gonna draw two different Fermi levels with excess carrier here and there. Okay? And don't worry, this will be gradually more and more clear as we go towards more. It is a little bit confusing, I totally understand. And if you're feeling a little bit confused, that's the right thing. If you feel like I got it completely, that means you're not really getting it. So it's okay. There is a little bit scope for confusion, and that's why it's the last slide, because we'll quickly go over the next lecture and we'll start seeing more of this quasi-Fermi level. And I hope that by the end of next lecture, things should be fully clear. If not, then you can worry about it and talk to me. I'll help you out. All right. And by the way, that's what I wrote here. We will consider the quasi-Fermi energy levels again when we discuss forward bias p-n junction. So hopefully by the time it will be clear. But just know that there is this concept of quasi-Fermi level, and you use different Fermi levels for electrons and holes when you have excess carrier. Okay. So that brings us to the end of this lecture, and let's move over to the next one right away, which is a more exciting lecture, I think. I guess you guys should probably be happy about it because finally you have started looking at devices with all those extra arguments about carriers and energy levels and quantum physics and whatnot. Finally, we arrive at a situation when we start seeing something tangible, something that you can play with in the lab. And I know that you have been playing with diodes already in the lab, I'm sure. And apparently for Mazhar's lecture, I already planned the lecture actually, but the lecture was supposed to come after this lecture, so that you have a little bit better idea about diode. So because of my sudden changes in the travel plan, I have to send him in the last class. So I hope it's not too confusing. You could still relate, but if there are confusions, I'll be more than happy to revisit that and help you make sense of the entire flow. So starting with PN junction diode, and there are a set of comments here. One important comment, and you could read it later on, but one important point that I'm going to highlight. But before that, let me just try to find an empty space to draw something. Imagine you have an N-type semiconductor and a P-type semiconductor, and you have been doing research on N-type semiconductor, trying to study how they behave when you apply different levels of voltages, and you are doing the same for P-type. So after a while, as a researcher, what would you do? Right? Will you just keep studying N-type and P-type individually? Wouldn't you think, what if we combine them together? What happens then, right? What if we had two different kinds of doping in the same material, N-type here and P-type here? How will they interact with each other, right? This is an obvious curiosity question, at least, for engineers or researchers. So at the very least, the easiest possible device that you could possibly try out. By the way, N-type semiconductor is still a material. It's not a device. P-type semiconductor is still a material, special type of modified material, but still a material. But when you bring these two different types of materials together, at any interface, when you create interface between different materials, that turns out to be a device. Okay, because that depends on the interaction between different materials. So you are dealing with the simplest possible material possible with semiconductors, the p-n junction diagram. So you might be feeling a little bit, disheartened. We are learning easy stuff, but that's what brings you to this point. Most semiconductor devices that you'll ever learn about will contain at least one junction between p-type and n-type semiconductor. So you're not just learning a p-n junction diode. By understanding the interactions in a p-n junction, not necessarily a diode, any p-n junction, you are actually setting yourself in the path to better understand any future devices that you might care about. Okay, because any semiconductor device will have at least one junction between p and n-type semiconductor. There are some minor exceptions, but for the vast majority, that's true. So semiconductor device characteristics and operation are intimately connected to these p-n junctions. So considerable attention will be devoted to the basic device. I just wanted to explain why we are taking this so seriously, because we are building towards more and more complicated devices. So whatever concept you learn about p-n junction, in the next set of lectures, you'll see BJT, which is just one extra layer of material, PNP or NPN. So you have two p-n junctions back to back. So that's how we are going to treat it. Instead of treating it like an entirely new device, we'll use our understanding of p-n junction and basically translate it over to the understanding of BJT and so on, right? So I hope that makes sense. Now, in a p-n junction, the interface must be something of great importance, and we'll spend a lot of time talking about the interface because that's where the action occurs. This interface has a name. It's called the metallurgical junction. Yes. A fancy name for the junction or the interface itself. And this is a representation of the doping concentration, an abrupt change in doping concentration at the interface, at the metallurgical junction. So for p-type semiconductor, you have a lot of acceptor. So this is the concentration of acceptor. And for n-type, you have a lot of donor. This is the concentration of donor. You see, there is an asymmetry. This is intentional. You could have it the other way. For example, you could have the same level of acceptor number and donor number. Doesn't matter. Or you could have more donor. For example, you could have more donor than acceptor. So this is not set in stone. This is just a representation that you could have different levels of dopings in the p-type side and the n-type side. Just to let you know. Now, Interestingly, since this is p-type, there will be a lot of holes. They're majority carrier. Since this is n-type, there will be a lot of electrons everywhere. So if you have heard, learned something in some of the previous lectures, diffusion is a natural process that occurs when there is a density gradient, when there is a difference in concentration. So when you see that many holes concentrated in one region and almost nothing on the other side, yeah, there are some minority carriers, but practically very negligible compared to the number of holes available in the p side. So the natural tendency for these holes would be to diffuse to the other side, right? And same applies to the electrons. The electrons will try to diffuse to the other side. And that's what you see. Hole diffusion, holes will try to diffuse in this direction towards the n-type, and electrons will try to diffuse in the other direction. That's the number one thing to consider. And because of the abruptness of the change, notice there's a lot of holes and almost nothing here. There is an abrupt change. If you remember the hole or electron diffusion current, the diffusion current was related to, say, for electron, remember the gradient, the density gradient. So if you have higher density here, lower density here, so this is a situation, say situation A, and let's draw another situation here, maybe situation B. Which one do you think will have a sharper, or higher diffusion current? I mean, I'm gonna answer for you. I know it's not convenient to ask and wait. The green one, option B, because that has a sharper transition. That has a sharper dn over dx, rate of change of density or density gradient, however you put it. So if you have sharper density gradient, you have more current, or you have more tendency of diffusion. So you can only imagine what happens. You have such an abrupt change. You have a lot of holes, and all on a sudden you have almost nothing. So there is an abrupt change. So this is definitely a significant motivation for the holes to diffuse inside n-type, and exactly opposite for the electrons from the inside. So they will start doing. The holes will start getting to the other side. Remember, this is the metallurgical junction. This was the junction. What are we looking at here? So the holes will move over to inside. They will diffuse. They will migrate to the inside because of diffusion force. And the electrons will diffuse from the inside to the p side. So then what? Then the question is, then what? So let me remind you of one thing. Let me just go here to the drawing board and remind you of one thing. Conduction band, valence band. This is the donor energy level. And apparently, this was the intrinsic Fermi level. The donor energy level would become our new Fermi level because the electrons will be up to this point at least. All right. Now, you might remember that when we excite electrons from the donor level and let them go to the conduction band, they leave behind what? So the electrons are negative charges, obviously, but when they leave the donors, they leave behind a positive charge. We talked about it before. These positive charges are static. They're stuck in the crystal. Because remember, say for arsenic and silicon, which arsenic is an n-type dopant. It has 5 electrons. It uses 4 to bond with the silicons, and the other is kind of free to go, right? So this is the 5th electron of arsenic, for example. If that electron is gone, all on a sudden, arsenic has 1 electron that what it naturally possesses. So this will end up becoming like a positive ion, but it's stuck because it's bonding with the other silicon. So it cannot move around, but it will still be positive charge, right? So when the donors give up electrons, they become positive charges, but they are stuck in the crystal. They're rigid, immovable charges. So let me start with this one. So when there are donors everywhere, this is an n-type material, donors everywhere. But these donors lost the electrons to diffusion. The electrons from these donors went to the other side, diffused to the p side, apparently. So these charges that you see here, these positive charges, they are the static positive charges appearing from the donors. And that's what you see, ND positive charge. This number of positive charges will be equal to the number of donors, almost like ideally. You might be wondering, why don't we see these positive charges all the time? Remember, when you just have N-type material, let me just go back. Sorry, I'm going back and forth. When you just have N-type material, say this is N-type. Yeah, you have electrons. You have those fixed charges that cannot move around, but the electrons are already also part of the same material. So if you have 3 electrons, you have 3 positive charges, so they are balanced. They are screened. They are screening each other, right? But if the electrons decide to migrate to the other side, all of a sudden this zone will have more positive charge than negative charge. So this zone will start behaving like a lump of positive charges concentrated in one position. Okay, so that's what you see here. They are all coming from the donors who gave up their electrons. And those electrons then eventually left the material, went to the other side. And exactly the same argument occurs to the p side. So we had acceptors before. The acceptors can accept electrons. They accepted the electrons. And now they're all negative charges. Because the holes left. The holes are positive charges. They used to screen the negative charges, but now they've moved over to the other side, leaving behind the static charges. So you end up with a set of positive static charge that are stuck, right? And you have a set of negative charges that are also stuck. They cannot move around. Unlike the electrons and holes, they're, they're stuck in one place. And there are interesting implications of having charge that is static and not moving. This charge difference. So imagine if you have a static positive and static negative charge somewhere, there will be an electric field generated from the positive to the negative side, electric field, right? So this separation of charges will lead to an internal electric field. And by the way, since this region is interesting, I was expecting a question, but I understand it's difficult to ask question in this situation. So I'm going to ask for you. How do I know that I have up to this point where the positive charges will pile up? Why not the entire N-type? Why not the entire P-type getting, these negative charges? Why are we stopping somewhere, here and here? The answer to this question lies here in this interaction. I'm going to talk about it now. So the more electrons diffuse to the p side, the more positive charges open up. Similarly, the more holes diffuse to the n side, more negative charges open up. And if you have, say, 3 positive, 3 negative, you have a certain amount of electric field. If you double the number, you can double the electric field, and so on. So you can increase the electric field strength by uncovering more and more charges. And by the way, I'm going to refer this as space charge from now on. It's not related to the space travel space. Space is in a sense that basically these are stuck at a given position. So their space is fixed. So that's why we're using the term space charge. Okay? And this region is often called the space charge region, wherever you have charge fixed in space. And that leads to an electric field generation. And that electric fields, obviously electric field affects charges, electrons and holes. And here is how they're going to affect the new set of charges. Let me show you. So for diffusion, you still have holes here in the p-type material. Diffusion will encourage the holes to go to the other side, to the right. And that's why you see diffusion force on holes will be in this direction. And the same, but opposite applies to electrons. Diffusion force will encourage electrons to go in this direction. And that's what you see here, the diffusion force on electrons. But the electric field will affect the electrons and holes in a different way. So because of this direction of electric field, it will hinder, the holes and stop them from coming to this side. Basically, these electric fields will act against the diffusion force. And if I'll get back to it for a second, but let me finish the other argument. But the same electric field will, exert an opposite force to the electrons as well. So this electric field is in such a direction that it will oppose the diffusion of holes as well as the diffusion of electrons. Okay? So they are unrelated process, by the way. Electric field acts differently than diffusion. But in the end, they're all acting on the same particles, holes and electrons. So they will affect them simultaneously. Now, you might be wondering, why did we have this initial diffusion then? Why didn't we stop right away? Because the electric field wasn't simply strong enough to overcome the diffusion force. The diffusion force is typically much stronger initially, but then as you uncover more and more charges, this electric field becomes stronger and stronger. And apparently at some point, the electric field perfectly balance the diffusion force from holes and electrons, and then they will stop. So you uncover up to a certain zone, uncover the charges up to a certain zone, and then you stop. Same applies to the other side. So this zone where you stop generating space charges and basically just stay there is called the space charge region. And there is a specific measurement that you could do. You could calculate and predict the size of the space charge region. And this is a very important and interesting zone to think about. That tells you whenever you connect, I mean, see how profound this impact could be. Whenever you connect an N-type and P-type material, no matter which device, diode or anything else, there will be a space charge region. You might be wondering, why is he taking so much time explaining that the electrons are diffusing, holes are diffusing? Because this is gonna occur in any device ever. So I'm doing so that I don't have to keep repeating the same discussion for BJT or MOSFET or others. Okay? So I hope that makes sense. And if there are any questions, don't hesitate to ask me now or later. So we understand that diffusion and electric field will work against each other in a space charge region. And based on that understanding, we are now gonna look at some, band diagrams and energy band diagram and try to see the device properties from a different perspective. Okay, so this is like a qualitative argument as to this is what happens when diffusion and electric field counterbalances each other, and you end up with a static situation, like stable situation. Okay, they don't just dynamically keep changing; they are stable at thermal equilibrium unless you apply some sort of external voltage. Remember, we haven't discussed applying any type of external voltage as of now. So you have absolutely zero voltage applied across it. Whatever is happening is because of the natural interaction between N-type and P-type material, nothing else. So thermal equilibrium, 100%. So now, let me go back here, and I like to use this drawing board more often for this. Imagine you have a P-type material here, and you have an N-type material here. Okay, notice one thing. Forgot to mark. This is conduction band, valence band, conduction band, valence band. If you notice something, that I try to keep the spacing between conduction and valence band the same. And you'd be right. That is deliberate. I'm keeping the difference between the conduction and valence band the same. Why is that? Because remember, the difference between conduction and valence band is the band gap. Okay? And band gap is the signature of a specific material. For example, silicon has a specific band gap. Germanium has a specific band gap. So when I say P-type, this is still P-type silicon. N-type, still N-type silicon. So the band gap doesn't change as long as you're dealing with just silicon. There are other more fancier devices that use different kinds of semiconductors. These are, heterojunctions. We'll have a lecture on that, a brief lecture on that. At some point, we'll discuss this. But for the most part, as long as you're just using silicon, these gaps will always remain the same. All right, remember that. Now, for P-type silicon, if I ask you, where should our Fermi level be? So if you draw the intrinsic Fermi level will be exactly in the middle for both of them. But for P-type, the Fermi level should be closer to the valence band. This is the actual Fermi level for P-type. And for the N-type, the Fermi level should be closer to the conduction band, okay, based on our previous understanding. Now, as long as they're two distinct separate materials, it doesn't matter. They can have two different Fermi levels and they're happy about it. But the moment you bring them in contact with each other, as we discussed in one of the previous lecture, remember, what happens when you connect two buckets of water, right? There will be redistribution, and at some point they will stabilize at a situation where the top level of the water, I mean, this is obviously an analogy, it's not necessarily the exact perfect analogy, but just a way to understand what's going to happen for this system. Electrons will move from one material to the other, and they will try to flatten out the Fermi level. They will try to achieve the a common Fermi level between the two levels. Let me clarify it a little bit. Conduction, valence band, conduction band, valence band. This is p-type, this is n-type. So for p-type, this is your Fermi level. For n-type, this is your Fermi level, right? When you bring them together, this Fermi level will basically come to one common level. And I'm gonna draw the band diagram starting from the Fermi level because that will be the only thing which is uniform across the stack. So this is our new Fermi level. Now, based on our previous understanding, let's draw the rest. Let's draw the conduction band and valence band for the p-type. So how far was the valence band from the Fermi level? Say x. Keep the same distance. So this is still your valence band. I mean, let me ask you a question, and maybe Uday can collect some answers from the students. My question is, why am I creating why am I keeping the same gap between the Fermi level and valence band before and after contact? This is before contact. This is after contact. After we brought them together, we created an interface between N and P. Why am I, keeping the valence band exactly at the same distance as was before? Any responses in the class?
Anyone?
Can anybody add a comment? You can be wrong. Like I said, there is nothing wrong with being wrong in the class.
Any guess?
How many of you remember that this distance is determined by the doping concentration, right? We discussed this many times. If you increase the doping concentration for p-type, this Fermi level will go down farther and farther. So the separation between Fermi level and valence band represents the doping level of the p-type material. Now, when you bring them together, when you bring p-type and n-type materials together, their doping levels will not change. The doping concentration will remain the same. So that's why you have the same separation. If you change the separation, that kind of represents that you have changed the doping level, which is not the case. All right. So I will keep EV fixed for the p-type side. And for the N side, which one should I keep fixed? EC, because the separation between EC and EF Fermi level represented the doping concentration for the N-type material. So I'm gonna keep it fixed. So this was EC. I'm gonna keep so maybe this was Y. I'll keep it Y, exactly the same. So I'm trying to draw it, keeping the scale meaningful. Now, how can I draw, given these two numbers, how can I draw the other band? For example, here, this is valence band. How can I draw the conduction band? And for here, this is conduction band. How can I draw the valence band? Turns out it's super easy. Remember, the band gap, the gap between EF and EV will always remain the same because it's the same material. Silicon is not going to change from a silicon to something else simply because you have merged them together, right? They will still be silicon. So keep the same spacing and draw the conduction band here. And here, this is conduction band already. So keep the same spacing and draw the valence band here. So you have conduction band, valence band. You have EG and EG. The only thing that I've done, which is, different than before, is that I have flattened out the Fermi level. So the Fermi level will be identical across the stack. Am I making sense? So just to clear up a little bit without completely erasing everything, let me draw something here. So we have a situation where you have a common Fermi level. You have conduction band, valence band in the N-type layer. You have conduction band, valence band, conduction band, valence band in the p-type layer. So what should we do about the interface? What should we do about the gap? How should they, be represented? For now, I'm gonna give you a simple answer so that you could just remember it and possibly say memorize for the time being. but I will show you mathematically why it is so. All right. So for the time being, just connect them gradually. Don't just abruptly connect them. They're not going to be like, let me show you. They're not going to be like abrupt, switching from one type of material to the other. Just make them gradual and connect them smoothly. And like I promised, you'll see the mathematical reasoning behind this smooth connection soon. And follow along the line. Why? Why am I following the same distance? Same argument. Band gap. This is silicon, so same band gap. This is silicon. Everywhere you have silicon. This is silicon. This is silicon. All of this is silicon. Even at the interface, no matter what happens at the interface, it still remains silicon. So the spacing should remain the same, e.g. So keep the same distance, and there you go. You have a really nice smooth transition from p-type material to n-type material. Does that make sense? One final time, because this is important. So if I ask you to draw the band diagram for a p-n junction, you start with a thermal equilibrium, by the way. We haven't even discussed what happens when you apply positive voltage or negative voltage. We'll discuss that soon. But for the time being, just stick to the thermal equilibrium. We start with the Fermi level. That's where we start, by the way. And then we draw, so you want to draw p-type here, n-type here, or let's actually change it a little bit so that you have a practice. So maybe this is n-type, this is p-type. So for n-type, I'm going to draw the conduction band close to the Fermi level and the valence band farther out, keeping in mind that there is a band gap. For p-type, I'll draw the valence band closer to the Fermi level and conduction band farther out, but still the same separation, e.g. band gap, right? And then I will connect these two gradually, and I will explain why that is gradual later on, but gradually keeping the same band gap everywhere. This should always be easy, right? This is nice and simple. But, as an engineer, can we start making sense of the shape that you have received here, the band gap, the band diagram shaping? Let me explain what. So this is n-type, this is p-type. In n-type material, you have Fermi level here, so you can easily create free electrons in the conduction band. Great, you have free electrons in the conduction band in n-type material. But do you think that a free electron will be able to easily go to the p-type material? Why or why not? So if you think about, in a very simplistic, conventional, classical analogy, if these are cars that are trying to go over this barrier, they will be stuck by the barrier unless you provide them enough energy to gradually climb up the mountain and go. They will be stuck here unless you provide them external energy to overcome the barrier. Okay. On the other hand, where are the holes? This is p-type material. The holes are here in the valence band. If these holes try to go to the other valence band, so holes flow through the valence band, electrons flow through the conduction band, right? When the holes try to go to the other side, they will see a barrier of exactly opposite type, and they will face the same problem. So they need, additional energy to go over the barrier as well. So this is like the flip problem for electron. Could be confusing because holes don't exist, as you know. They are basically just a particle that we made up to make our life easier, to explain the process in an easier way. So just stick to the barrier for electrons. So you see there is an energy barrier. And let me now get back to this slide. And I hope now you'll be able to understand the origin of this diagram. It doesn't come out of the sky, automatically. You can easily reproduce this property. One thing that I didn't show you, let me quickly draw that again. So here we have a p-type here, n-type here. I'm just going to do exactly that. P-type here, n-type here. For p-type, you have this type of a situation. For n-type, you have this type of a situation. And then you merge this together gradually, right? One thing that I didn't talk about is intrinsic Fermi level. It's easy to draw, by the way. Just take the midpoint everywhere, midpoint. Even here in the gradual transition, that's your intrinsic Fermi level. We still draw it so that it acts like an origin kind of thing. It's like a reference point so that you understand where the other things are. Okay. So intrinsic Fermi level will be midway all across the material. Now, looking at this one, if this is n-type, there will be electrons here, and the electrons will face a barrier. And we can measure the barrier. This is the barrier. Okay, this is a barrier. We often call it a barrier height, or we can call it built-in potential that restricts the flow of charges from one side to the other. This is built into the device. You haven't even applied no external voltage. So nobody is resisting the flow of electrons or aiding the flow of electrons. It's just the device itself. So it's built into the device. You might be wondering, okay, we'll come to that question later, but let me just finish this thought first. So this built-in potential is represented as VBI, built-in potential. Yeah, and that is more like a measurement of the amount of barrier that the electrons has to go over to get to the other side. Okay, even when you apply some sort of voltages, say maybe you apply a negative voltage to encourage the electrons to go to the other side, they will still have to go over this barrier to get to the other side. So if your negative voltage is not high enough to make them go over the barrier, nothing will happen. So how many of you remember diode turn on voltage? So if you look at the current voltage property of a diode, it takes up to a certain voltage for the diode to turn on, right? And after that, it turns on and gives you current. So that turn on voltage is directly linked with this built-in potential. So you have to first overcome the built-in potential to even start having any action at all. So this is this diode drop is determined by the built-in potential. So this is a very important parameter. Now, getting back to the question that I was about to ask you, why do we have this built-in potential, right? You must have seen, I mean, we ended up with this shape. I mean, we didn't even think about having a barrier in the first place. All we were trying to do was balance out the Fermi level, right? We tried to make it flat across different materials, and we just followed along all the other obvious things. If you have a Fermi level, your valence band and conduction positions are going to be the same as before, similar here, and you have to maintain the same band gap. So just connect them. We ended up with a barrier, right? It's not deliberate, but it was natural. Well, who led to this barrier? Why did we have this barrier? Well, that can be answered by saying that who helped you flatten out the Fermi level? Were the Fermi level, at the same level before? No. As you remember, for p-type, it was here. For n-type, it was here. N-type, p-type. Right? This was the Fermi level. This was the Fermi level. They were not at the same level. How did they come to the same level? By redistributing carrier. So some carriers went here, some carriers went there, and eventually they came to a common point. This is the Fermi level balanced out. And this flow of carrier from one direction to the other is directly a testament to what we just discussed here. So this is another way to discuss the same thing using band diagram, right? In a band diagram situation, when the carriers are flowing from one side to the other, they're trying to balance out the Fermi level. They're trying to come to one common agreement so that the Fermi level is standard, uniform across the device, right? And in doing so, charges are flowing from one direction to the other. Yes, we talk about diffusion and electric field, counterbalancing each other, but the way we represent perfect balance is by showing that your Fermi level is flat. So when your Fermi level is flat, that's when you have perfect balance. That's when the device is stable. So two sides of the same coin. They're all pointing to the same process, but using two different strategy, using two different levels of depth. Okay, I hope that makes sense. One more thing before I move over to the next slide. This is a measurement of the built-in potential, as you see. Oftentimes in textbook, you'll see instead of VBI, they'll have EVBI. E is the charge of electron. Why? Because they like to express this in form of electron volt. If you multiply the voltage with charge of electron, you can easily get, this is electron volt unit. So don't feel intimidated by this at all. This is a very simple expression. For some reason, semiconductor folks try to use electron volt instead of joule as measurement of energy. And one more thing, how many of you remember, I mean, we discussed this before, say conduction band, valence band, intrinsic Fermi level, and then Fermi level. So the difference between the Fermi level and intrinsic Fermi level uh, could be mathematically expressed, and we expressed that in one of the previous lectures. You can always review that lecture and remind yourself the equation. But apparently, you could calculate the separation between the Fermi level and intrinsic Fermi level in the T side as well as the N side. Notice the action occurs within this zone near the interface. Deeper into the material, it's essentially as if nothing happened. This is the conventional P type. This is conventional N type. Nothing happened, right? Only here in the space charge region, things became strange, like curved band, all sorts of other things. So inside the material, all the other equations that you saw before combining N and P together will still hold. So will here. So a strategy to calculate the built-in potential is, instead of measuring the curve here, you could measure the curve in the intrinsic Fermi level, because the intrinsic Fermi level will bend by the same amount. Why? Because the intrinsic Fermi level is basically following the curve, right? As you remember, it's Eg over 2, basically, right? So if you take the bending of the intrinsic Fermi level, instead of calculating this, you end up with the same number. So that's what we do. Because it's easier for us to calculate the bend in the intrinsic Fermi level. Here is why. You have an equation to calculate the separation here, deeper into the material. You have a way to calculate the separation here, deeper into the other material. If you add these two things up, you could calculate the total barrier, you see? So that's what you'll see in the textbook. Anyways, I'm not going to the math. I'm trying to reduce, math-based distractions moving forward, because we're now already in the device level. So remember, with some simple calculations, you can add these two things up, and that's what I show here to get the built-in potential. And you can do the calculation. This is detailed in the textbook, and you arrive at a situation where you get this equation where the built-in potential is related to the number of acceptor, number of donor. So acceptor concentration and donor concentration could be tuned to change the built-in potential. Now, as an engineer, that should give you something to play with. So what if I want more built-in potential, higher built-in potential, or lower built-in potential? How can I do that? By changing the doping. One more thing, you can also change the material. You can go from silicon to germanium. And what will that change? That will change the intrinsic carrier concentration. So also shows up here. So that's how you can also change. And KT over Q or KT over E, as I've told you many times, this is just the thermal voltage. So oftentimes in many textbooks, you see VT instead of KT over E. All right. So this is the measurement of built-in potential. I think this is a good point for us to stop, because we are almost out of time. I think I'm happy that we could at least get to built-in potential. We'll do the math problem. All right, maybe let's finish the math problem. The math problem just asks you to calculate built-in potential at a given temperature. Sure, put in the temperature here in the KT over Q. They have given you the concentration of donor or acceptor. Put in those things as well. They said that this is silicon. You know the intrinsic carrier concentration for silicon. There you go. You have BBI, built-in potential. Perfect. So that was easy, rather than just keeping it for the next class. So we are done with that. We'll start with charge density and electric field calculation in the next lecture. Thank you so much for listening in and for your patience. And I hope to see you all in the next class. And I remember that October 1st, there will be no class. So I'll post an announcement.